Oh, that's funny. I think this is the turn-in file.
This is the chapter 5 one, right?
Yeah, I think that was
Okay.
lab 5, the chemical reactions.
Okay. How was last week?
Last week was the moles and chemical formulas, so that was 2 weeks ago. Because we did the Epsom salts last week.
Okay. So the one that I missed was last week, but it wasn't online. This was the one I could find, so I did this one.
I guess I'm confused, because you gotta make it up in person though, so I don't want you to do it off of the videos, even if you did, so you have to do it.
Okay,
Yeah.
that makes sense. Okay.
Yeah, I just didn't remove the videos, because I still teach this class online.
Okay,
Occasionally.
so I did an extra one then?
I guess, you tell me. And then, yeah, you should have come in today to make up the
well, that's
lab.
why I didn't come in today, because I
Well,
just did that one.
you should have checked, because I don't allow people to make them up online anyways, so
Okay, so.
I would have told you that. So you can come in next week on your non-lab day to make it up.
I can't because I work.
And I don't know, we'll have to, are you free on Fridays? We'll have to figure out a
I
time.
work every day but Wednesdays because I have a
Yeah, I mean, we could try to squeeze it in then with one of your other labs.
Okay.
Why is it so dark? Why does everything just make it darker? No, I don't want that light on.
So it was really just two things, dark and darker.
Okay, that kind of works. All right, so today we're just going to lecture since we missed Monday, and then I decided to not give y'all a quiz, so we'll just use the whole 2 hours for trying to get through this chapter, since it is a lot. I can't remember if we talked about redox reactions. All right, so probably not. So we left up on stoichiometry. All right, so we'll start off with our redox reactions. And okay, well, what is this? So these are oxidation reduction reactions, so also called redox for short. And so this is any reaction where electrons are transferred from one reactant to another. So again, they're called oxidation reduction or redox. And so we can look at some of these. And so actually, before we start kind of analyzing this, we should go over a few starting places. And so if we're looking at this, so let's kind of start off. We're going to skip down for a second because we need to understand our rules. And so kind of the first rule here, and a good starting point to talk about, is that a free element is considered to have an oxidation state of 0. And so this is something that's just in its elemental form. And so, right, that means that, you know, however it's found on the periodic table by itself, so in this case, right, chlorine, we know that that's a diatomic, so in its elemental form, again, by itself, it's Cl2. And so, right, that would mean like sodium as a metal, so not in a compound. And so now let's go back to our example here. So looking at this example, we have iron metal, so that means it starts off in a 0 oxidation state. And then we're starting with, again, oxygen. So again, elemental state, right? O2, diatomic, it's a gas. So starting off is 0 for oxidation state. And then so they combine together. And so we know that in a compound, oxygen usually takes a -2 oxidation state. So then figuring this one out, so it looks like iron has to be 3+. And so now we can start to piece together kind of what happened. I'm actually going to rewrite this so we can have some space. So we said, okay, we're looking at this 4 equivalents of iron plus 3 equivalents of oxygen give us our iron oxide. And so, okay, now we're kind of piecing things together. And so just think back to, again, how metals behave, right? Metals tend to give up their electrons. We've been seeing this in just our common oxidation states. And so, yes, this is what's going on. So we have iron 0, and then it's going to have to lose 3 electrons. Plus 3 electrons, right? So it gave up those electrons to become iron 3+. And then, so the question is, well, where did those electrons go? So, okay, now we can examine our oxygen in more detail. And so again, it made this iron oxide. And so each oxygen itself, so let me do 1/2 equivalent. So each oxygen has to gain 2 electrons to become oxygen 2-. And so now we can start to see not only do we have a balanced equation, but our stoichiometry should match also with our electrons. So we have 4 equivalents of iron here, losing 3 electrons, right? So we have 12 electrons total in this process, right, from our 4 irons. And then with our oxygen, right, we have 6 of them total, so each of them gaining 2 electrons, so 6 times 2 gives us 12 electrons as well. And so, right, it makes sense that it should be balanced. This is something else to think about for the future, that you have to balance, again, the electrons. It won't be that big of an issue in this class, but kind of something to keep in mind. And so again, right, we're seeing that behavior where the metal is supplying the electrons, right? Again, that's what we've been seeing, that the metal gives up those electrons. So the iron lost 12 electrons total with, again, 4 equivalents of iron, and then the electrons were picked up by the oxygen. So that's, again, right, the important part of the redox. So we can say, well, iron is giving electrons, right? So that means that our oxygen is receiving. And so we can kind of analyze these other ones as well, so we don't have to go as in depth. Let's skip this combustion one for a second. So let's take a look at this easy one. So H2 plus O2 gives us water. So like we saw in our balloon reaction, again, both of these starting in their elemental forms, and then obviously hydrogen becoming 1 plus and oxygen 2 minus. So again, you can see right where hydrogen is supplying those electrons for oxygen. And so I skipped the combustion for now. We'll come back to it and analyze it in a second. And at least we can appreciate that a combustion reaction is a redox reaction. So kind of a hint with that is you're adding oxygen to carbon. But again, we'll look at that more formally. So we saw this reaction. And so again, just kind of recapping what happened. So again, if one is losing electrons, the other must accept them. And then we can bring in some extra terms too. So atoms that lose electrons are being oxidized. So if we think back to this iron plus O2 gives us iron oxide. Now I'm just not balancing it. But right then we can say, okay, well the iron, right, was oxidized because again it lost electrons, right? And then, okay, well our oxygen is being reduced since it gained electrons. And again, that's your other hint is, so anytime you add oxygen to something, then usually it's oxidized, and again, the math works out in this case, right? So we added oxygen to iron, so therefore iron was oxidized. Makes sense so far? And so now we can take a look again at this sodium plus chlorine reaction. Again, everything starting off in its elemental form. So we have sodium metal, right? Nice piece of solid found in nature as by itself. Then we're adding chlorine gas to it, again in its elemental form, so oxidation state of 0. And okay, we know in a compound, right, sodium is going to take a 1 plus oxidation state. Our halogens are always -1. That all makes sense. Then we can put together our electronic bookkeeping and our terms, so we can say, right, our sodium was oxidized since it lost electrons, and our chlorine gained electrons. It's not too bad. And then we'll do some quick mnemonics as well, just to help you remember. And so I'll give you 2 options. And so I'm from the South, from Texas, so we love oil there. So we like oil rig. So this one stands for oxidation is losing electrons, and that means reduction is gaining. So we have that mnemonic. And if you're just not a big fan of the oil industry or want something else, I have another one. So we have Leo goes GR. And it depends what your favorite, I guess fuzzy big cat would be. I used to work somewhere where they were the leopards, so it was Leo, the leopard goes GR, but you can change it to lion. And so that's going to stand for losing electrons is oxidation, and gaining electrons is reduction. So that will at least kind of help you remember which one's oxidizing, which one's reduction. Okay. Got those copied down?
No.
Oh, okay, I'll give you. Oh, no, no worries. Get those copied.
That was recorded.
So we got those written, or are you still?
I'm good.
All right, so now the rest of this kind of page is just kind of identifying our oxidation states. And so let's go through these rules for assigning oxidation states, and then we'll go back to that combustion one. And okay, so we started off with the first rule. So okay, free elements have an oxidation state of 0. So right, that just means in their elemental form, how they're found in nature by themselves. And so then the next rule is kind of, okay, then our monoatomic ions have an oxidation state equal to their charge. And so that mainly refers to, right, our group 1 and 2, and then of course, right, like aluminum, so all our standard ones, zinc. So that's just their charge. And then of course, just like before, right, when we're writing our ionic compounds, we know that they have to be neutral. So our sum of our oxidation states should equal either the sum of our compound, so obviously 0, right, if it's a molecule, or we'll add or overall charge, right, in case it's a polyatomic. So it should equal the charge of the polyatomic, which we'll see a little example. And so then the rest of it is kind of goes by these priority rules. And so this little chart helps you. So fluorine is always -1 for our purposes, right? So fluorine extremely electronegative, so it's always going to be -1. Hydrogen is usually 1+, but there is an exception. And so that's going to be the metal hydrides, or anytime you see this hydride. So that means that it's H-1, which is unusual. So we could have like aluminum trihydride. That would be where hydrogen is -1, or any sort of metal hydride, so iron dihydride. So again, we don't see too many examples of this, but just be aware of that. And okay, oxygen, this is one that we usually base our other oxidation states off of. So oxygen is always -2, except if it's a peroxide. Let me draw my exception somewhere. So exception, peroxide. So a peroxide, let's just start with our known peroxide. So hydrogen peroxide is this. And basically a peroxide has this O2 2-, so such that each individual oxygen is -1. So that's a peroxide definition. And the more general form of a peroxide is this. So basically, right, you have 2 oxygens single bonded together, and then they can be bound to anything else. So the R could be a carbon, a hydrogen, or some other atom, so it doesn't matter. So as long as you have two oxygens next to each other, single bonded like that, that's a peroxide. And so again, each oxygen is -1 in that case, so that's an exception. And then the rest follow pretty normally, so group 7 are halogens, -1, are group 6, -2, obviously, so that's the rest of the oxygen analogs. Then nitrogen, -3, or other group 5s. And so it did point out, again, our oxidation states for nitrate then. And so the starting point for this one is base it off of the oxygen. So oxygen is, again, always -2 unless it's peroxide. And so that leaves nitrogen with +5 then. And so, right, nitrogen can kind of do that switch as well of -3 and +5. So we can see that. Blah, blah, blah. Oh, other terms. So then we can also have the term reducing agent, which is going to be the element that's oxidized. So same name. And so, okay, if we look at this back to our other example. So now I'm going to squeeze in the iron reaction again that we had looked at initially. So, okay, again, iron plus oxygen gives us iron oxide. And what we had said that the iron went from 0 to iron 3+. And so, yes, right, we already said that it was oxidized. But we can use this other term as well that's called reducing agent. So it's the reactant that reduces an element. So it's supplying the electrons. And that's another way to think about it, right? So supplies electrons. So again, right, it's probably the metal. So that's your other hint. So now we're going to call iron our reducing agent. And so if iron was our reducing agent, and this kind of makes sense, especially for this case, because it's oxygen, and well, oxygen, right, it was reduced, but it's also our oxidizing agent. Since, again, it accepted the electrons, so that makes it our oxidizing agent. So again, watch those terms. And then recapping for our sodium one. So again, right, sodium was oxidized. It went from 0 to 1+, so it lost electrons. And so that means that it was the reducing agent as it supplied the electrons. Okay, kind of, any questions, on that, kind of overall? And then let's look back at that combustion one that I had mentioned. And so kind of the other thing to keep in mind is, so right, if it's an ionic compound, then yes, the oxidation state actually corresponds to measurable charges, while otherwise it's just more of a kind of electronic bookkeeping. And so it really becomes electronic bookkeeping, especially when we look at organic structures, and especially right in this class with our limitations. And so based off of this information, we don't have a structure for this, so we're just going to have to mathematically determine our oxidation state of carbon. And so again, the caveat with this is without a structure, you could get some weird oxidation states for carbon, but that's fine because again, it's just electronic bookkeeping at this point. And so let's go through this, what I mean. And so we'll start with oxygen. So that's obvious, right? It's in its elemental form. So that's going to be 0 for its oxidation state initially. And so now let's calculate it for carbon. And so let's base it off of our hydrogen. So hydrogen, we said, is always 1 plus. And let me bust out my little calculator for this. And so, okay, this has to be 0. So that means we have positive 18, right? So 1 times 18. Then I want to solve for what my charge has to equal to. So obviously, my 8 carbons have to equal 18, right? So now I'm just going to divide by 8. So that means each carbon is in an oxidation state, and that should be negative 2.25, right? So let's just redo that. So 2.25 then, so negative 2.25, excuse me, times 8. So that gives us back to negative 18, right, which balances with that 18 there. So does that make sense for the first part there? So all we did, right, was just like before, we know we need a neutral compound. So I based it off of our hydrogen, set up our algebra, and again, that's how we got negative 2.25. And so again, we're just saying that this is the average oxidation state of all these carbons. Again, we don't have a structure, so we can't individually analyze it. So again, that's fine for our purposes. And so then let's continue with what happens. So hydrogen doesn't change oxidation states, right? So still 1 plus 1 plus. But then oxygen goes from 0 to negative 2. So right, that's consistent in either one of these compounds, so that's good. And then obviously carbon now becomes plus 4. And then if you wanted to, I could prove to you how the number of electrons is the same, but I don't know if that's interesting. All right, do we feel okay about redox? Kind of, we'll keep practicing.
It'll take some getting used to.
Yeah, everything takes practice. All right, so now we'll shift to the rest of chapter 6. And I put the chapter 6 homework up front so you can grab it. And so now we want to shift to energy. So that's kind of our big picture topic of this chapter. And so energy is just defined as the capacity to do work. And that means like work in the physical sense, right? So actually the definition of performing work. And right, energy can be exchanged between objects, so through collisions, it can be exchanged obviously through heat, right? There's a lot of heat exchange in chemistry. And then work, if you haven't taken physics, at least this is a basic definition of work. So it's force acting over a distance. And you can correlate your energy then that is needed, right, to perform that work. And so we could also say that this is path dependent. And again, like I said, we'll be looking at heat in this chapter as well. So looking at that flow of energy caused by the difference in temperature. And so heat and work are two different ways then that an object can exchange energy. So either a system, like a chemical system, could perform work, or again, right, heat could be exchanged. So we'll look at that. And okay, well, let's start with just what is energy. So we have, right, kinetic energy. So of course, that's the energy that's associated with motion. We could, do our basic kinetic energy equation. Kinetic energy is 1/2 mv squared. So you don't really need to know that, but at least just kind of, right, appreciate what is kinetic energy. We could also talk about right? That even like electrons in a current, in a circuit, right? That's kinetic energy of your electrons literally moving around. And so thermal energy is just a form of kinetic energy. So it's related, of course, to the temperature. I don't have the equation on the top of my head, but there's a relationship between energy and, again, temperature. So we can correlate that. Let's see. And then, so of course, we'll also talk about potential energy. And usually, right, you might be thinking of like gravitational potential energy. So, right, that's energy kind of associated with a position, right, in relationship to the Earth. So, okay, I have my pen, I'm holding my pen, right, it has the highest amount of gravitational potential energy here. And then, of course, if I release it, that potential energy is converted to kinetic energy. Except in here, right, we're probably not going to be talking about that. What we're interested in is, right, the energy more associated with the composition. So we're interested in, right, the energy in bonds. So either breaking or making bonds, which is one thing that we'll talk about. So making, breaking bonds, but also disrupting intermolecular forces, which takes less energy, but again, we'll get into that. And again, that's intermolecular, so between molecules. So we care about that, right? And you can kind of think about it as big picture concept. If, you know, obviously, maybe you ate some lunch or something, and well, where do those calories come from? They are like stored within the, right, the bonds of your food. So then you're converting all that potential food energy into hopefully kinetic energy as you run around. And then, so just other kind of forms of energy to help you classify. So like we mentioned, so again, electrical is a form of kinetic energy. So again, right, that movement associated with the flow of the electrical charge. Heat or thermal energy, again, that's kinetic energy, since that's related to molecular motion. You know, we've kind of mentioned this concept of absolute zero as well, which will be coming back for thermodynamic relevance. Light or radiant energy, so that's also kinetic energy. And then the last two are both potential energy. So either, right, nuclear, so we could talk about the energy that's stored in the nuclear forces, right? So obviously, when you do decay, that can release energy, which is usually used to then, right, heat up water and spin the turbines of your nuclear plant. Or we'll, again, mainly be focusing on our chemical potential energy, again, based off of our structure from the bonds and so forth. All right, so then we have to, again, orient ourselves. And so this is why I like looking at this equation again with this kinetic energy, because it tells us where the heck the joule units come from. And so if we break this down, so again, kinetic energy is given by this 1/2 mv squared. And then in physics, mass is always given in kilograms. And this is v for velocity, so that's meters per second. And so now we can plug this in, so 1/2 kilogram meters over second squared, which gives us this, right? So kilograms meters squared over second squared, which is equal to a joule or a Newton meter. So this would be if you cared about work over a distance, you might see this in Newton meters. But for our purposes, will mainly be in joules. So just know that a joule, though, has the units of kilograms meters squared over second squared, because this might help you with dimensional analysis. And so then here, the work part comes into play. So then again, we can translate it to work. So then this is saying that 1 joule of energy is the amount of energy needed to move 1 kilogram mass at a speed of 1 meter per second, right? So you can imagine taking that mass and moving it, so that would take, right, a joule of energy. And then, so kind of more units to think about. And so we can relate it to the calorie, except, oh, this is kind of depressing news, or at least I thought it was depressing. So we have this little calorie. So notice, right, this is lowercase, and this is defined as the amount of energy needed to raise the temperature of 1 gram of water 1 degree Celsius. And then a kcal is needed to, the energy needed to raise 1,000 grams of water. And so now the depressing part is that your food calorie is 1,000 little calories. So that's a lot of calories. So that energy can add up, again, when you think about it. And so then more energy conversions. So we have one little calorie, so not your food calorie, is then equal to 4.184 joules. And then, like we said, the kilocalorie is 1,000 calories, which is also equal to, like I mentioned, your food calorie. So now you can be depressed. And then, I don't know, don't you feel depressed that, like, there's that many calories? I've felt depressed about it. Like, maybe it's just me. I guess you can be excited about it, your energy. You can go calculate it. And then if you wanted to think about kilowatt hours, if you can translate that from your electric bill to joules. So 1 kilowatt hour is 3.6 times 10 to the 6 joules. So that's kind of fun. All right, so then we have our first law of thermodynamics. So, right, well, if we're going to talk about energy, we got to talk about basically our ground rules. And so our first law of thermodynamics is the conservation of energy. And so that means the total energy in the universe is constant, and so it is conserved. And right, so we can think about it even, again, from consuming our calories. So right, it started off as potential energy, and then it becomes, right, kinetic energy, which then is also lost as heat. And then, right, so from this first law of thermodynamics, this also tells us that we could never design a system that will continue to produce energy without some sort of source of energy. And then you've heard of, like, because this goes into, like, all those, like, theories. So then I wanted to bring up, like, this perpetual motion machine, right, where it was kind of this theory that people had, this hypothetical machine that, like, oh, could you have a machine that could somehow power itself? And, we can just tell from our first law of thermodynamics that this is impossible. So again, kind of fun to think about, right? But then we're going to see, okay, you actually lose, again, a lot of efficiency. All right, so then let's start getting into some of that potential energy that we mentioned and quantifying it. And so, of course, our chemical reactions involve breaking bonds in our reactant molecules and then forming new bonds. And so then we can figure out delta H, which is our change in enthalpy, aka heat, basically, or energy. And so we can figure out basically how favorable this bond making or breaking process is. And so then we have just our bond energies that are formally calculated. And so this just describes to you kind of where these numbers came from. So again, the amount of energy it takes to break 1 mole of our bond is called our bond energy. And so these are all calculated in the gas state and then homolytically. So what that means is that we have, right, normal bonds such that when they break, right, each atom gets half the bonding electrons. So, right, we're looking at hydrogen. So if it's homolytic, right, it's going to break evenly. So it's always assuming a homolytic break. So not every bond is homolytic, but we won't worry about that right now. And then, so for our purposes, bond breaking is endothermic. So, right, you have to put energy in to break a bond. And so that's where we get a positive sign. So again, right, you're putting energy into the system. Maybe add that. So energy in. And then bond making is exothermic. So usually this is a favorable process, and their orbitals are lowered. And so that's why we get energy released. So, and it would be released in this case as a form of heat, right? So if it was favorable, it'd be exothermic, and then it'd be hot, so it'd be releasing that energy again as heat. And so then we can find that we can, again, calculate our change in enthalpy for our reaction just by summing up our bonds broken and then adding them to our bonds formed. Again, where the breaking ones have that positive value because we're putting energy in, and then making them gives us our negative value. So kind of have that key there. And so for these problems, you'd have to be given a chart, but we also want to just make some general notes. So, okay, the more electrons they share, then the stronger the bond. And I probably should have mentioned this when we talked about it, but so when you go from single, double to triple, the bond length also tends to decrease, right? So it gets shorter as we go from a single to a triple. And so also reflected in that trend is the energy, right? So a single bond is much lower in energy versus a triple bond, right, which is much greater in energy. So that kind of makes sense here. And then same thing, so if you have a shorter covalent bond, then it tends to be stronger. And so a lot of this is just a sterics argument, but our bromine-fluorine bond we can see is a little bit stronger than our bromine-bromine bond. But again, right, you'd need a chart to actually do these problems, so your book should probably have a chart. And then other things to note when using this chart, so we have CO, right, C double bond O is usually 736, so that would be like in this sort of scenario. And then notice we have an exception, though, of 799 for CO2. So we should use this value for CO2. So let's try to do this example problem. So we'll do this one kind of together. So first it's kind of walking you through visually what's happening and what we're doing, right? So it's saying, okay, well, we're going to figure out what we're going to break. So this is our starting material, right? We're going to put in energy to break our bonds, so we can determine that. And then we're going to make a carbon-chlorine bond and a hydrogen-chlorine bond, and then get that energy back out. And so like I said, we'll do this together right now. But for this one, for doing these problems, it might be good just to start off with kind of writing out like what is even happening, so you can really visually see like what's being broken, what's being formed. Okay, and then there's CO2. All right, so then, right, maybe just highlight what we need to change. So I'm noticing here from our problem, right, we started off with methane, but now it became CO2. So it looks like we're going to have to break 4 carbon-hydrogen bonds. So I'll just kind of lay out what we're going to do. So we need to break 4 CH bonds. And then, okay, we're going to break, looks like we're breaking all these OH bonds, right? Because there's no OHs connected. So now we're going to do that. So 4 OH bonds. So we need to calculate that. And then look at what we have to make then. So before I let you try to look at these values, right? So then we're making 4 HH bonds. And right there, single. And then we also need to make 2 CO bonds. Now see if you can get those values from the chart. And then, so I'll keep doing it in case you can't see it. So right from there, then let's go to the chart. So we said, okay, we have to break 4 CH bonds. So then we look at our chart. Okay, each CH bond is 414. So 414. No, I forgot if that was in kilojoules. And then we also said we had to break our OH bonds. So obviously we need to multiply it by 4 still. So OH, let's look at what that is, if I can find it. There we are, so 464. Oops. And so let's start, we can just figure out how much energy we needed to break these bonds. So 414 times 4 plus 464 times 4. All right, so we have to put in 3,512 kilojoules. So again, right, big positive sign there. So we're putting energy in. And so let's see how much we got back out. So, okay, we said we made our HH bond. So let's go back to our chart. So 436. And then remember we have to use our special value for CO2. So 799. So let's see how that compares. So now 799 times 2 plus our 436 times 4, sorry. And so that means that we get 3,342 joules out. So negative. So now to figure out, right, our overall enthalpy change, we can add these two numbers together. So I'm just going to multiply it by -1 real quick. And now add 3,512. And so this overall process took then 170 kilojoules, right, per this reaction, so. And so we can also add some terms to it. So this is endothermic. So endothermic meaning that we had to put energy in. So right, we had overall positive. So energy has to go in. All right, let's take a little 10-minute break for now.
Be back at 2:00.
And then I'll try to hand back some papers.
I have to move my car, so hopefully I'll be back in 10
Okay.
minutes, but you never know.
Yeah, no worries. Yeah, I think it's pretty short, so let me know if there's anything else or anything. Yeah, of course. Last week's? Okay, we could do that.
Do you want me to just turn this in also? This is not else has this one too, but I know that this was last week, so I'm confused. I just got this from the chapter 5, so I don't know.
Yeah, I don't have the blackboard quite updated.
Okay, so should I just turn this in?
So did you do the lab though physically?
Huh?
Did you do the lab physically?
Yeah,
Okay.
like all the testing of the reactions and stuff. Yeah, I got the some classes. And then I rewatched the videos to make sure I did it.
Yeah, but you did it in class though, right?
Yeah, this.
Okay, yeah, so that's fine.
I did it double, and then I just missed months. But I didn't
Yeah.
realize I was doing the lab either like that.
No.
Again. So this. But this is on 4.
Trying to think.
Are we turning this on?
Because the
Because I
mold one
missed,
was lab 6, so that's lab 5.
So I missed lab 6, which
Yeah.
was last week. Okay.
Yeah.
Got it, okay. I was just using Blackboard, and I think that's what confused me.
Yeah, I gotta check the syllabus. I don't know, I spend so much time like getting the syllabus perfect, and then no one looks at the syllabus, and then it doesn't help that we switched from regular.
The computer program. I think that like messed up.
Yeah, well, it doesn't help because they kind of destroyed my formatting for the things.
Cause like, there was a point where I didn't realize that the computer system was messed up, you know? So when I went to look at my grade, it just shocked me.
Oh,
And
yeah.
I was like, wait a second.
Well, that doesn't help either.
Yeah, so.
So chapter 6 homework is due next week though?
Yeah,
Okay,
yeah,
okay. But we're a week ahead in lab.
yeah, because we skipped this week in lab. All right, did we all make it back? All right, so we'll keep looking at this. And so now we have these energy diagrams. And so this is just a visual way of kind of showing you what's happening as we go from reactants to products. And so in this case, we're looking at, again, this combustion reaction, so just combining carbon plus oxygen to give us CO2. And so again, right, we can look at our enthalpy of our reactants, and then we notice that our overall products are lower in energy. So again, you could do this by adding up all the bonds. And so again, in this case, we find that the CO2 has lower energy. So we can tell, okay, if it went from higher energy to lower energy, then this is an exothermic reaction. And so then, right, the other thing is, okay, well, let's say you were holding this reaction. So obviously, right, it's releasing energy. But like we said from our first law of thermodynamics, well, then that energy basically has to go somewhere. So if our energy left our system, where your system is your reaction, then it is transferred to these surroundings. So again, thinking about this, okay, it would be exothermic, so then it would feel hot in your hand, right, as your hand is being warmed up by the heat. And so this is another diagram that probably you'll see on like an exam or something. And so on an exam as well, you might have to kind of draw and label the different parts. And so we start off with our reactants. And so again, let me relabel this just so it's clear. So this is an exothermic reaction diagram. So we have time on our x-axis, energy on our y. And so, right, we know it's exothermic since our products are lower in energy. And then we would be able to either label or write our change in enthalpy. So that is our difference, right, from our reactant to our product line, since this is, again, energy on the y. And so let's look at this. So, okay, starting again from just our 0 point in time, so we have reactants. And then notice we have this activation energy and transition state. So, right, our activation energy is just basically our energy kind of needed to get our reaction going. And then our transition state is, again, some sort of temporary fleeting state that's either, you know, where bonds are being made or broken. But this, again, is just going to be fleeting, and then higher energy, obviously, and then it goes back down to its products. So again, you could label your activation energy, which goes from your reactants to your transition state. Then we have our transition state where, you know, bonds are being broken and exchanged or formed, and then down to our products here. And so now looking at this for an endothermic process. And so just looking at the opposite, so if we could decompose the CO2 back to carbon and oxygen, what would that look like? And so now our products are higher in energy than our reactants. So that means energy has to go into the system. So endothermic reaction. And so again, with these endothermic processes, then they're going to feel cold to us. And so you can kind of think about like those icy patches, right, that you have. So usually it's like ammonium chloride, and then you just bust the seal and it starts dissolving it. But dissolving ammonium chloride takes energy, so that's why it feels cold, right? So your body is supplying the energy needed for that icy pack. And again, right, if you're surrounding, so you are the surroundings, so obviously it's going to feel cold as that energy, right, goes into the system there. So again, we're just emphasizing, right, energy just flows from one part to the next. And so again, we can look at our reaction scheme for our endothermic reaction. So, right, we know it's endothermic because our products are higher in energy. We can still calculate, right, our change in enthalpy, so difference from reactants to products. And then just like before, we have our activation energy and our transition state. It's just our products, again, are higher in energy than our reactants. That makes sense. You have some homework problems where it asks you to like sketch these out. All right, so then kind of covering a lot in here, again, just like touching on all these ideas. And so with thermodynamics, we also kind of have kinetics, so somewhat related, but also separate. And so our rate of reaction is just a measure of how fast the reaction makes products or uses reactants. And the ability to control your speed of the chemical reaction is also important. So you may not want the reaction to happen too fast either, you know, especially if there's something like extremely exothermic or maybe gas evolution, right? You might want to control that so that it doesn't go too crazy. And so again, these are just kind of how to affect reaction rate, just kind of in general. And so the greater the concentration of reactant molecules, right, the faster the reaction. And I think you'll play with this later, but this would go into like how 3 molar reacts faster than 1 molar. And like I said, I think you'll do that in another lab. So you'll basically race how long it takes to dissolve magnesium with 3 molar acid versus 1 molar. So again, higher concentration just means there, you know, more collisions, more productive collisions happening, so more reactions. And so this also applies to gases. And so of course, the higher the pressure for gases as well, and the higher the concentration. And so now just kind of thinking to the Haber-Bosch process. So I've mentioned this reaction before. So this is just H2 plus N2 to give us ammonia is the Haber-Bosch reaction. And so why I like talking about this so much is obviously it's really important because this is how you make fertilizer on an industrial scale. But part of the kind of caveat of this reaction is, again, it's also has to be forced, requires a lot of energy. And so as you might imagine, this reaction is run at pretty high pressures. And so that goes back to this concept, right? High pressures to get that reaction to go, so higher concentration. And so concentrations, again, also apply to molarity, which we've been kind of dancing around this topic of molarity, but we'll formally cover it in the next week or so. But again, like we'll see, so higher molarity, higher the concentration, the faster it reacts. And so temperature can also affect reaction rate. And this is just, again, a really general statement that it makes. So it just claims that for every 10 degrees rise in temperature, the reaction of the speed tends to double. Again, that's just very general. So all we're saying is we can increase the temperature and potentially increase the reaction rate. All right, so then looking at the next thing that we cover in here. So it mentions a catalyst. And so does anybody know what a catalyst is? What do you think of? Yeah.
Something that, it's the thing that initiates a certain reaction or process.
Yeah, initiates or like usually speeds up or helps out.
Like the starting point or something?
Yeah, well, it usually like provides kind of a mechanism is really the,
Like here in sentences, this was the catalyst of, this process. That's where I hear it.
yeah, and when it's referring to that, right, so the important part of the catalyst is, right, it's helping to kind of accelerate our reaction. Oh, somebody brought up enzymes as well, right? So enzymes could be a catalyst, right, like a, now I just blanked out on the saliva. Is it amylase that's in your saliva?
Yeah,
Yeah, so, right, like the amylase starts breaking down
the sugars.
the sugars, exactly. Let's look up some other catalysts.
Bromelain or whatever, what is it called?
Which,
I think it's like in pineapple juice or something like that.
oh, I probably don't know, but you're probably right. There's got to be like, I think you're right. The pineapple has some juice or some enzyme. I'm just not sure what at the moment. And okay, so let's look at our kind of general definition, but then we'll look at some catalysts. And so basically, right, they're substances that affect a rate without being consumed. And so how they work, and I think this is really the important part, is they provide an alternative mechanism for the reaction. And so it has, oh, so somebody in the chat says it's bromelain is the enzyme. Is that what you were referring to? Oh, cool. I'll have to look it up because I'm not familiar with it. And so let's kind of look at what this means. So we can first start with just these equations. And so this is a reaction that could potentially take place in the atmosphere, in like the ozone. And so this is ozone, and again, this is going to be happening in pretty small scales. And so right, this is ozone reacting with radical oxygen to give us O2. And this is a pretty slow reaction, which is what I would expect. And if we add a catalyst, though, so this is where we could start going down the rabbit hole of volatile organic compounds and like why halogens could be potentially more dangerous in the atmosphere.
Yeah, chlorine gas, we've seen examples of that in World War I.
Yeah, well, that starts to go down the rabbit hole. At first, they used it to kill people, and then obviously the after effects of like putting those halogens in the atmosphere. So, right, again, even on a small scale, so you can have a bit of chlorine radicals then, and then they react with your ozone to make O2, and then this intermediate species, right? So this is just an intermediate, and then the CLO goes on to react with another equivalent of oxygen to give us O2, and then our catalyst of chlorine back out. So that's nice. But so some other things to think about is, again, right, it's creating a different step here. And so, if you've taken biology, sometimes you kind of see this like oversimplified, like, active site here with our catalyst. And then, right, it sort of binds or provides some sort of substrate, right, for your reaction to occur. So this could be reaction, right, that's catalyzed. And that's kind of nice. Oh, do you have a question?
No, sorry.
This is just, again, kind of an oversimplification. So I wanted to at least put it in a more, like, tangible chemistry context. And so these grub catalysts are pretty famous for olefin metathesis. But again, the key point that we want to point out is that it provides a new pathway. So let's see if we can find Yeah, so here's kind of an example of our intermediate here, right? So we start off with our ruthenium catalyst, and then it takes our substrate here and it binds to our metal, right? So that's how it's providing a new pathway in this case for, so it's binding, so it has a place to bind, and then, right, reaction can occur, and then new product is formed. So then it does an elimination from this. But again, right, the point is just to say, new mechanism, right, it's binding in a new way because now it can react with the ruthenium, bind it there, and then continue on to make the product. That's kind of fun. I'm trying to see if there's more mechanism ones. So again, here's another, just kind of showing you the intermediate. So right, starting material, boom, right, new mechanistic pathway because it's binding to our catalyst, and then catalyst does action, spits out product here. So again, just kind of appreciating how that couldn't happen without a catalyst. And so we could also see this in kind of our energy pathway. And so again, right, uncatalyzed pathway, one transition state. And then, so this is not to say that, right, you'll necessarily get two transition states, but what it's trying to emphasize is, right, new pathway, and that's why it has a lower transition state. And, right, there might be multiple pathways. So with the reaction it was referring to, right, it has these two steps, so that's why they kind of had two humps, but that's just kind of an example. But basically, right, your transition state is lowered, such that, right, that activation energy is less. And let's see, other terms that we should go over. So again, we said catalysts were not consumed, and as you probably gathered, right, most catalysts speed up reactions, and so sometimes they're used positive catalysts. And then you could also have a negative catalyst. Can you think of it, what else a negative catalyst could be called? Like another name for it? What did you say? Not a buffer. What about inhibitor?
Insulator?
It's usually like inhibitor is like, I think, the biology term. Because insulator is more like thermal stuff, but maybe you haven't used that term in biology of just something that like inhibits a pathway or like something that's competing even. Yeah, so I think that would be, again, I'm not the best biologist, but some sort of inhibitors, right? So something that would mess up the active site, so then that would potentially, right, slow down your reaction of something.
Like the surge protector on a computer.
I don't know if that's a good analogy. I'd have a better chance of looking up an inhibitor. Oh, come on. Yeah, so like something that it brings up would be like a drug used to prevent like the treatment of HIV spread. So that would act as an inhibitor towards HIV, like that sort of thing. And then, so other terms we should talk about are homogeneous versus heterogeneous catalysts. And so homogeneous catalyst refers to all species present in the same phase. And so with that, I would kind of put this, put the Grubbs catalyst under there, or like any sort of, basically what I used to do, so like organometallic catalyst, trying to make stuff. And so basically with the homogeneous catalysts, they're all in solution, or, you know, they could all be in the gas phase, obviously, but generally this is solution chemistry. So you can think back, okay, it's similar to like these Grubbs reactions, how they would work. And so kind of the thing to understand, again, big picture idea of this homogeneous versus heterogeneous catalyst is, well, always the question with a catalyst, right? Well, we said the catalyst is not consumed. So then the question is, how do you recover this catalyst, right? And so sometimes it can't be recovered, especially in the case of a homogeneous catalyst. Again, right, when you have something like this, it's just in your reaction mixture and it's really not feasible to try to recover this catalyst. And so this is where it goes into like loading efficiencies too. So just looking at this example here, how it says 0.05 equivalents, right? So basically, you only have 0.05 equivalents of that catalyst. So that helps bring your costs down, right, if you can't recover it. And so I'll add that to homogeneous, so hard to recover the catalyst. Not always impossible, right, but that's just something that if you were on an industrial scale, you'd be trying to figure out is like, can we fish this catalyst back out or is it trash? And so that's where the heterogeneous catalyst tends to work better. And so some example of this would be your car catalytic converter. So your car catalytic converter, right, is like a solid phase of some sort of, I think it's platinum or palladium metal. And then, right, gas gets passed over it, and then it gets cleaned up by your catalyst. And again, obviously, right, they're in different phases since you have a gas versus a solid, but then recovery is usually easier too with these heterogeneous catalysts, and especially, right, obviously in the case of a car catalytic converter, you know what it looks like, people can steal it, but yeah, you could recover it. So kind of the next thing to throw in here is this concept of chemical equilibrium. And so the example that they give is hemoglobin, right? So your hemoglobin is, of course, your protein, right, that is found in red blood cells. And so it mainly binds to the iron, but it wants us to, of course, think about this as a dynamic equilibrium. And so first of all, let's note our equilibrium arrows, right? So there's these half arrows. So that is equilibrium. And so, right, you could compare that to the double-headed arrow of resonance. So resonance shows just like electron movement. I'm trying to show resonance versus. And then equilibrium is saying that we could go back and forth between these two reactions. And then, right, single-headed arrow is obviously just in one direction in general, right? That's what it means. It's usually it goes to completion. And okay, so now we're looking at these equilibrium arrows. And so again, that means it's something is in dynamic equilibrium, meaning again, it can go back and forth. And so let's kind of think about how this would work in our bloodstream, right? And so maybe we start off in the lungs, and so just kind of think about how that works. So obviously, like your hemoglobin starts off without oxygen, but then if it's in the lungs, we're going to have a high concentration of oxygen. And so that high concentration is going to lead it to bind, right? So then you have this kind of bound hemoglobin, oxygen. And so then this travels right out to your body. And so then it goes out into the world. And so now we'll just kind of, right now we'll say, so now in our leg, so now we have, right, our hemoglobin is bound. But then, okay, once it gets to the leg, right, it's going to be in an environment where there's no oxygen, right, because your leg already consumed the oxygen moving. And so now in this environment where there's less oxygen, now this hemoglobin, right, is going to re-dissociate. So deposit some oxygen in your leg or other extremities. And then, of course, right, your hemoglobin will come back and go back to the lungs to repeat the process over again. And so it just does that, right, over and over and over. Oh, so there were our arrow conventions. I got overexcited. And so with this, we at least want to be able to express an equilibrium constant in this class. And so let's look at how we translate that. And so, right, this would be our balanced equation here. So we start off with our balanced equation. And then note, okay, products go on top, so it's products over reactants. And then these little brackets refer to concentration, usually in molarity. And then notice, right, they're raised to the power of their coefficient here, right? So that's just their little coefficients from balancing. And then it's our equilibrium constant, so we can help compare. And then our K value is unitless. And so now we want to practice writing our expression. So then we can see, so we're looking at this dissociation and reassociation problem. So we have this dimer that can split off and then create an equivalent of oxygen. And so again, how this is set up, so obviously these are our reactants, right, products. And then obviously I displayed the answer, but we can, follow along. So right, products over reactants, we have our concentration of NO2 to the power of 4, right, times O2. And then over our reactants, so that's N2O5, and again, right, raised to the power of 2 from our balanced equation. So that's all you have to know how to do, and then maybe the next extension of that would be if I gave you values for these, you might just have to solve, but we won't really go that much further. And then we just want to look at, well, what do these numbers at least kind of tell us, at least in general? And so now let's kind of look at these reactions. And okay, when it's saying when K is much, much greater than 1, when the reaction equals equilibrium, there'll be more product molecules than reactant. Well, okay, just think about that, right? So we said K was in general, products over reactants, right? So we don't have to worry so much about the little squaring details. We just need to take, okay, products over reactants. So if K is much, much greater than 1, right, that means we have a lot more products. So that's what it's saying here. So now looking at this, kind of how we apply it, okay, we're looking at this reaction, H2 plus bromine gives me HBr, and then we're trying to figure out, right, is that favorable? And okay, the K value for this is actually crazy large, right? 1.9 times 10 to the 19th. So pretty large, and all that is to tell you, right, is that it's probably going all the way to the right mainly, right? So it's mainly going to completion, so I expect that most of our hydrogen and most of our bromine is fully converted to HBr. And okay, well, let's look at the opposite. So what happens if our value is much, much less than 1? So again, just think about this. Simplify products over reactants. Well, if it's much less than 1, then we must have a lot of reactants, right? And so, okay, let's look at this scenario. So N2 plus O2 gives us NO. except the K value for that is 4.1 times 10 to the negative 31. And that should make you feel pretty good though, right? Because otherwise, if this reaction was favorable, we wouldn't have much oxygen left over to breathe, so.
So when K is less than 1, there's more reactants in products, and then for K is greater than 1, it's opposite?
Yeah. Yeah, and you can always, right, just kind of put your ratio. So, yeah, if K is less than 1, then we have much more reactants and products. And then, of course, right, we, again, may not see this, but if we have a K close to 1, obviously, then you have, right, pretty similar products and reactants. Again, roughly speaking, right? Like I'm not accounting for equivalence and anything, just kind of saying, well, if it's generally close to 1, then they're going to be pretty much even, right? That product reactants, products. So. And so then we want to be able to take kind of these thoughts with equilibrium and kind of take it a little step further. And it sounds fancy, but if you just kind of think through it, it makes sense. And, okay, so it's saying basically what happens when we disturb our equilibrium. And so first of all, right, it's saying that once a reaction is at equilibrium, concentrations of the reactants and products remain the same. And so, right, if it's at equilibrium, so let's look at a graph actually. There's a lot of words on this part. And so I like this graph here. And so right here, right, we're at equilibrium. So our concentration of NO2 and N2O4 are remaining the same. And so that being said, right, we're not saying that no reactions are taking place, right? So on a molecular level, there's still a bunch of action going of, right, dimers forming and splitting, but we're just saying overall, right, the equilibrium is undisturbed. Okay, so that's our first set of conditions that we need to understand. But then it asks, okay, well, if we change our conditions, right, then basically our system is going to work to restore equilibrium. And so what it's saying is, right, we'll perturb something, and then the concentrations of all our other chemicals will change as well. Again, we'll kind of break this down because there's a lot of words. And so, right, our new concentrations will be different, but our equilibrium constant will be the same, unless we change the temperature, but we won't be changing the temperature in here. And so again, for our purposes, I'm not going to make you calculate a bunch of stuff, so that is, we'll say that for my 200 level class, but you just kind of want to be able to understand how Le Chatelet's principle applies. And so, right, what we want to say is, okay, once our system is disturbed, basically, can you predict which way it will shift? And then, of course, by nature, obviously, disturbing it makes our system open. And so now let's kind of go through a few of these scenarios. And again, we might have to practice more next week if we need to wrap up all these ideas. And so let's look, I like looking at the graph here. And so it says, after equilibrium is established, a reactant is added as long as the added reactant is included in the equilibrium constant expression. And so it's adding that it's not a solid or a liquid. So, right, it has to be some sort of aqueous solution, some sort of concentration that we're changing. And so we're talking about like not a solid reagent, so not a pile of like carbon, So it doesn't matter how much you change that pile of carbon, the concentration doesn't change. Or it could be gas, so I don't want to forget gas. And then, so this is kind of confusing for a second, so let's skip this and look at our graph and what it was saying. And so let's look at what it's trying to show us. So we have our equation here. And so this is, again, just a dimerization and reversing of that. So we have N2O4 that splits into NO2. So this is considered our reactant in this case. And so let's look at that scenario where it says reactants are added, which is going to be on our right here. So, okay, notice initially we're at equilibrium, right? So our concentrations are the same. And then we have artificially, right, spiked our system now. So we've added in a bunch of reactants. And so just kind of thinking about it from Le Chatelier's principle, or what we're trying to say is, well, if we're adding more reactants, right, then it's probably going to cause more products to form, right? So if we add more reactants, then it's going to want to split. And so that's what happens. And so it mentions that. So let's go back to the text for a second. And so it's saying, okay, how will this affect the rate of the forward reaction? And so again, right, initially, our new reactant is going to increase the rate of our forward reactant since we literally have more in there. But then no initial effect on the reverse reaction since we don't have any products added. And so then the reaction proceeds to the right until our equilibrium is restored. And so let's again see that graphically. So okay, that matches up, right? So we artificially perturbed our system. Now we can see our concentration of NO2 rising, which again we expected. And then the next thing that it mentions is kind of what happens to all our values. And so, right, how does it affect it? So, of course, at our new equilibrium position, so what it's saying is, well, now we have more products, right? Because we added more reactants, so then now it's going to make more products. And then it says we have less of the non-added reactants, so that makes sense, right? Like if we had a second reagent in there, then that would have to be consumed to make more products. And then obviously we have less of the added reactant. And so yes, let's see that verified. So okay, that matches up, right? Again, we artificially spiked it, so concentration of NO2 went up, concentration of N2O4 went down until our new equilibrium is established, right? And so now we have greater concentrations of both our reactant and our product, but all that matters is, again, equilibrium is reestablished, and again, that K is constant. So if you were in my 200 level class, you'd be doing some math, but we'll just kind of appreciate the effects. And so we could, of course, remove reactants, so that would cause it to go reverse. So they didn't remove reactants in this case, but they added our products. So again, you can see a similar effect. Obviously, if you were to remove NO2, right, that would also cause your N2O4 to go to the right and disassociate more to make up for that loss. And so blah, blah, blah. So again, like we said, K will remain unchanged. And so other things to think about is, well, how does this help us, right, in kind of real chemistry life? And so I'll bring up some examples. So let's look up. And so this is a Dean Stark apparatus. And so this is used when you have a condensation reaction. So a condensation reaction, basically, the really basics of a condensation reaction is that you put two things together, so A plus B, but then water is formed plus whatever product, your desired product. And so then the question is, well, how do you get this reaction to go? And so we can use Le Chatelier's principle, though, with our Dean Stark. So that's what this is used for. So we would have our two little reactions in here, and then we have this reflux condenser that's then attached to this Dean Stark. And so if we look at this Dean Stark, what it is it's like this extra tube here, and this one has a stopcock, so most of them have some sort of stopcock where you could release this liquid. So the idea is you use some sort of organic, probably, well, it has to be less dense than water if you're going to drive off water. But then you start doing your little reaction, and so then your Dean Stark, right, fills up. So you have your little Dean Stark over here. So reaction, right, condenses. So you have all these condensers on there. But then this is your Dean Stark trap, and this is, right, opening. And so the idea is that you'll get water on the bottom, which is why you should pick your solvents wisely. And then let's just say ether, because ether is a commonly used solvent, or any sort of organic that's less dense. And so then, right, you have your water collecting over here, and so you could even drain it off. So the most important part is that your water is no longer in this reaction flask, but obviously you can drain it out even further so that there's no, chance of it dripping back in if you fill it all the way. And all that's doing then, so right, you remove the water so that you can keep this condensation reaction moving forward. So even though, right, you're not removing the desired product, as long as you're removing the water, then that's going to keep driving this reaction forward. And so, like some condensation reactions can take like a long time, like 3 days of heating. And so what's going to drive that is, again, this Dean Stark and driving that water off. So that's how you can use Le Chatelier's principle to help your reactions. All right. Any questions or anything? Trying to look at our oh. So we only have like 5 minutes or so. I'm just trying to pull up the homework to see if there's anything crazy. So obviously, right, number 1, it tells you to use the table so you can compare bond energies. So this is all using your bond tables, catalysts, so a lot of definitions. These would be good to go over, just make sure you understand that. Oh, this is what I was talking about with making those energy diagrams where you have to sketch it out. So this is good practice because I'm pretty sure I'll make you do one on the final as well. And then, yeah, this is more Le Chatelier's principle stuff. So I feel like the homework should be pretty straightforward this week. to it, even though we kind of rushed through. Any other questions or anything? So we'll probably end here, but like I said, right, ask me questions, look over the homework. I think it should be straightforward, even though we kind of had to cram this chapter in. Yeah, it was a lot of stuff, but remember, we're also just kind of getting big picture ideas on like a lot of things. So like you can kind of see where the 200 level we could really dive deep, but here we're just trying to get big picture ideas, so trying to keep it simple. All right, well, we'll end it here. Thanks again. So no quiz this week. And then probably next week we'll try to quiz over stoichiometry and this. Yeah. All right, thanks again. And then I have a lot of papers for y'all, so make sure that I hand back your papers. All right, I'm going to stop this stream.